My name is Fabio Streun, and I've been working on this project with Joel Wanner and Adrian Perrick. So virtual private networks are really used to secure the communication over the internet, and they're widely used by corporations as well as by private individuals, and often serve as the main access point to protected services and resources on the internet. There are various solutions out there for the consumers, different implementations, different protocols, like WireGuard, OpenVPN, IPsec, Cisco AnyConnect, and so on. And if you want to know how well the implementations and protocols perform, there are plenty of benchmarks out there to look at. And these benchmarks often consider a setup where a VPN client connects to a VPN server over the public internet, and that they measure metrics like throughput, latency, CPU utilization, and so on. These are all really important metrics to ensure that the deployment and implementation meets the deployment's requirement. However, such benchmarks don't consider an attacker in the setup. And so the question arises, how resilient are VPN implementations against attacks? In our research, we look at 4 different VPN implementations: WireGuard, the IPsec-based strongSwan implementation, OpenVPN, and Cisco's AnyConnect. And we evaluated their resilience against certain DOS attacks. So to get started, I would like to give a brief overview of the VPN protocols and common DOS mitigation mechanisms. So a VPN protocol can usually be divided into 2 parts, the handshake and the data transport part. During the handshake, the client and the server authenticate each other and generate keys. The generated keys are then used to further authenticate and encrypt the data transport between the peers. During the handshake, significant processing resources are required and memory is allocated. And therefore, an attacker which floods the server with initiation requests could exhaust its resources and cause a denial of service. The VPN protocols and implementation mitigate such attacks in various ways. For example, source blocking and rate limiting in combination with address binding cookie mechanism are really common. Also, some protocols make use of pre-shared keys to be protected against external adversaries. Implementations often try to prioritize the processing of authenticated traffic over the processing of unauthenticated traffic. And they also use multi-threading to increase not only performance, but also DOS resilience. For example, the IPsec-based VPNs commonly use the IPv2 protocol for the handshake to mitigate resource exhaustion attacks, in particular memory exhaustion attacks due to a flood of initiation requests. Implementations enforce IP-based rate limits. However, such limits are not really sufficient against an attacker which can spoof its IP address. Therefore, there is a cookie mechanism provided by IPv2 which protects against, can I go one back, sorry. Yeah, which protects against spoofing attacks. Also the WireGuard protocol applies IP-based rate limits and a cookie mechanism to be protected against the same kind of attacks. Additionally, WireGuard also leverages the public keys of the peers which are shared between the peers beforehand. During the handshake, all of the packets are authenticated with a message authentication code which is calculated using the receiver's public key. So an attacker which does not know the receiver's public key cannot easily generate valid packets. The protocol used by OpenVPN is more or less TLS over UDP. And to protect the TLS handshake, various mechanisms are provided by OpenVPN. The mechanisms rely on keys shared between the peers beforehand, and the peers are then used to authenticate and encrypt the packets so that an attacker, again, cannot generate valid requests and handshake packets if it's not in possession of such keys. Also, there's Cisco AnyConnect SSL-based VPN makes use of cookie mechanisms to protect the TLS connection as well as the DTLS connection. So knowing that all protocols have DOS mitigations in place, we would like to evaluate their effectiveness in the implementations. For our evaluation, we used a setup consisting of 3 machines. 2 were running the VPN implementations. 1 was a VPN client, which connected to the VPN server. The 3rd machine was an attacker, which flooded the server with various kinds of packets. During the flooding attacks, we measured the throughput between the VPN client and the VPN server, as well as the time required for the VPN client to connect to the server. With these measurements, we were able to evaluate the resilience of the different implementations against certain DOS attacks. Important to note here is the machines are connected over 40 gigabit network, and the main device under test, the VPN server, is a commodity server equipped with 2 Intel Xeon CPUs, providing a total of 72 logical cores. Since we are working on multi-core system, receive side scaling becomes really important. Receive side scaling is a mechanism that distributes the processing of received packets among different cores. Typically, the hash over the 4-tuple IP addresses, TCP, UDP ports are used to determine the core which is processing the packet. So concerning the flooding attacks, we therefore considered 3 different flow configurations. In the single flow attack, the attacker always uses the same IP address and port number. Therefore, all the attack packets are mapped always to the same core, which is likely to be a different core that the packets from the client are mapped to. In the multi-flow configuration, the attacker uses multiple IP addresses and port numbers, such that RSS distributes all the attack packets among all the available cores on the system. In the 3rd configuration we considered was a client flow configuration where the attacker uses the same IP address and port number as the attacker uses the same IP and port number as the client does, so that RSS maps the attack packets to the same core as the client packets are mapped to. So let's start with taking a look at WireGuard. So on this slide, we see how well WireGuard handles a flood of initiation requests. On the y-axis, we see the attack rate at which the attacker floods the server with the initiation request packets. On the y-axis, and we have then the measured throughput and the measured connection setup time. The plots show clearly that throughput between the VPN client and the server can be denied with roughly 1.6 gigabits per second of attack traffic when sent over multiple flows. When the attacker sends the packets over the client flow, only about 600 megabits per second of attack traffic are required. To consistently deny connection establishment during the attack duration, which is about 25 seconds, we need about 20 gigabits per second of attack traffic. To put these measurements into context, we also established a baseline. In the baseline, we flooded the server with generic UDP packets of the same size and to the same port, such that we can see the limitations introduced by the hardware as well as by the kernel processing the packets. So we clearly see that the hardware as well as the kernel processing can handle much more traffic, attack traffic, without significantly affecting the functionality of the VPN. So to understand how a flood of handshake initiation packets can impact the processing of data packets, the processing of already authenticated packets, we have to look at the implementation of WireGuard. In short, WireGuard tries to achieve high performance by utilizing all the available cores on the system. When we profile the server by flooding it with initiation requests over multiple flows, we observe that the 72 cores spend up to 90% of the runtime in spin locks. These spin locks are in place to coordinate the distribution of the handshake packets or the attacker's packets to all of the available cores on the system. So the big number of threads accessing the same data structure is here the main bottleneck and cause for the performance. With the client flow configuration, the profiling revealed that the receiving core can be overwhelmed. The receiving core spends significant portion of the time waking up the other threads, which should then further process the attacker's packet. This indicates that the multi-threading is not really optimized with respect to malicious traffic. So instead of just flooding the server with initiation request packets, we also looked into automating the exploration of other attacks. Therefore, we implemented an algorithm that expects a list of packets which can be used to flood the server, and then figures out a mix with which it can disturb a VPN connection with the least amount of attack traffic as possible. So we applied this to WireGuard and the algorithm, and then found a packet mix which disrupts the VPN connection with just 750 megabits per second or 300 megabits per second of attack traffic in the multi-flow or the client flow configuration respectively. The mix clearly favors handshake packets over data packets. And especially interestingly here is that the cookie response packet is really important in the mix. The cookie response packet, the cookie reply packet, is the smallest handshake packet. So this clearly indicates also that the handshake packet rate is the main factor, is really significant for this attack's effectiveness against the VPN implementation. So coming now to the evaluation of the IPsec-based strongSwan implementation. When we flood the server with initiation requests, we see that an already established connection cannot that easily be denied. On the other hand, connection establishment is denied with just about 75 megabits per second of attack traffic, independently of the flow configuration used by the attacker. So that only the connection establishment is affected by the attack can be partially be explained by looking at the implementation. With strongSwan, the data packets are processed in the kernel. On the other hand, the handshake packets are processed in the user space, where one receiver receives all the packets and then distributes the work among other cores. A flood of initiation packets then is able to overwhelm the receiving thread and then also causes others clients not being able to connect to the server. The data transfer, on the other hand, is not affected by the attack then. When we want to take a look at OpenVPN, we see that our evaluation revealed that 100 megabits per second of attack traffic consisting of initiation requests is sufficient to overwhelm the system. Throughput as well as connection establishment can be denied. Also, the provided different TLS protection mechanisms from OpenVPN are not really changing anything in those measurements. So OpenVPN's implementation runs just on a single core and processes handshake packets as well as data packets. Therefore, a flood of handshake packets also impacts the processing of the data packets. So Cisco's AnyConnect VPN solution offers a IPsec-based VPN connection as well as an SSL-based VPN connection. So first, we look at the resilience of the IPsec implementation. Just as for strongSwan, we see that flooding the server with initiation requests mainly affects the connection establishment of the client and not the data processing, the data transfer processing from the packets from the client to the server. 50 megabits per second are sufficient to deny the other clients from connecting to the server. To deny throughput, roughly 5 gigabits per second of attack traffic are required. In contrast to the strongSwan implementation, we see that also the generic UDP packets have quite some effect on the functionality of the VPN. So therefore, we also flooded it with minimal size UDP packets. And we can see that here, with 300 megabits per second of attack traffic, the throughput is denied between the client and the server. The evaluation of this SSL-based VPN solution also shows similar things. The minimal size UDP packets are really effective to overwhelm the server. With 50 megabits per second of attack traffic, an already established connection can be denied, and with 200 megabits per second of attack traffic, connection establishment can also be denied. So coming to the conclusion, so how resilient are the VPN implementations against DOS attacks? Our research has revealed that with little amount of attack traffic, essential functionalities of widely used state-of-the-art VPN implementations can be denied. Further, and sadly I didn't have time to go into that, we found multiple additional vulnerabilities. This includes DOS vulnerable ITE cookie mechanism in strongSwan, as well as a single packet DOS attack for OpenVPN. Overall, we think that there is a lack of adversarial tests and benchmarks, and for the future we hope that more adversarial tests and benchmarks are going to motivate the development of software which are more resilient against DOS attacks. Thank you for your attention, and I'll be happy to answer the questions.